So these concepts guide us, like how we can understand the data, how we can make predictions, and how we can measure our success in these models. Basically, without statistics, machine learning would be like trying to navigate a road trip without looking at a map. So you might keep driving, but you won't know where you are going or how you get there efficiently. So my name is Busra Ecem Sakar, and I'm the Senior Data Analyst MolIQ. And I'm really excited to be presenting this talk as a part of Women Coding community. And this platform is all about empowering and supporting one another. And I hope today's session gives you useful ideas about the statistical basics that make machine learning better and smarter. So let's dive in. Let's take a look at the structure of today's session. First, in the introduction parts, we will begin with the overview of why statistics plays such a crucial role in machine learning. Descriptive statistics, we will discuss how we summarize and understand our data, which is the foundation for building models. And after that, we will explore probability, which help us make predictions and understand unknown outcomes in machine learning. Then we will move into regression, where we will explore relationship between variables and see how regression models work in practice. Then finally, we will look at how we can measure the performance of our models to ensure they are reliable and effective. And at the end, there will be a time for your questions. So feel free to ask. I love to discuss them all together. And let's start with a big question. Why do we need statistics in machine learning? Statistics is foundation of understanding and optimizing machine learning models. It helps us, as I say before, interpret the data we are working with and identify patterns and validate our results. So essentially, statistics provides the tools we need to draw meaningful insights from the data. And it helps us answer key questions like how do we summarize and understand our data? Here, concepts like mean, median, variance, standard deviation come into play. Or another question, how likely is an event to occur? This is where probability theory guides our predictions and decision making. And then what relationship exists between variables? So regression analysis help us uncover these relationships and build predictive models. And at the end, how do we check if our models works well? And we use metrics like accuracy, precision, recall, mean absolute error, R-square to make sure our models are reliable and effective. So as we go through this talk, we will explore how each of these statistical tools contributes to creating better machine learning solutions. So let's continue. I want to talk about first descriptive statistics, which is basically all about summarizing and understanding data. So in this slide, we are looking at test scores for 15 students represented by the dots on the graph. So x-axis shows the student numbers and the y-axis shows their scores. And the red dashed line represents the mean, which is the average score across all student score, calculated as, let's say, 69. And the mean gives us a sense of the central value of the datasets. The green dashed line represents the median, which is the middle score when if the data is sorted, in the middle of data is median. And in this case, median is 70. This means half of the students score above 70 and half of the score below. So unlike the mean, the median isn't affected by extremely high or low scores because it's just in the middle of value. And the gray vertical lines from each dot to the mean represent the differences between actual score and the mean, sorry, which contributes to the variance. The variance tell us how spread out the data is. And when we take square root of it, we will get standard deviation. The shaded orange region shows one standard deviation above and below the mean, which is the range where our most scores fall in if the data is normally distributed. So in this case, the range is approximately 52 to 85. But why does this matter for machine learning? So understanding these spreads or central tendency and outliers in our data help us to decide how we can continue our pre-processes and analyze the data before building models. But as you can see, we choose one standard deviation above and below the mean. But why do we choose this? So this is actually a really useful concept, and it all comes down to understanding how reliable our data is and how confident we are in predictions. Let me talk shortly about the empirical rule. It tells us that if the most of data points fall within one standard deviation of the mean, it's a good sign because it's shown that our data is consistent and reliable. Think of like if you are measuring students' test scores and most of them clustered around the average score, and that average is pretty good summary of how the students are performing. But what if some of the scores are really far away from the mean, like way higher or lower? If you have got lots of scores outside the 2 or 3 standard deviations, it could mean your data has more variability, or even some of them is outliers. So these tell us that maybe the mean isn't best measure to represent our data. And I want to talk about also confidence. This is where things get interesting. The empirical rule is also connected to something called confidence intervals. So confidence intervals tell us how certain we are about the range in which a value is likely to fall. So here's how it works. If we are talking about 68% confidence, it means there's a 68% chance that the value will fall within one standard deviation of the mean. So in simple terms, if you are predicting students' test scores, you can be fairly confident that most of the scores will fall in this range. But if you want to be more confidence, like 95% confidence, you will have to expand this range to 2 standard deviations. And this gives you a broader range, but more certainty that the actual values are going to be in there. So why is all this matter? Why they are so important? This rule is all about understanding how reliable our data is and how consistent it is and how certain we are about predictions. It's also really helpful in machine learning, knowing your data, how spread out or tightly clustered data is. It is important because it's help us to decide if we need to pre-process the data or do we want to handle our outliers, or do we need to normalize our data before feeding into a model? Let's move another topics. The probability. It is one of the most fundamental ideas in statistics and machine learning. Probability measures how likely an event is to happen, and it ranges from 0, which is impossible, to 1, certain. So, for example, the probability of flipping a coin and getting heads is 0.5 because there are 2 equally likely outcomes. So in machine learning, we often deal with probability distributions, which I first want to explain it. And these distributions describe how probabilities are spread over possible outcomes. So in this slide, we are focusing on 2 key distributions, the normal distribution and Bernoulli distributions. Let's take a look at the graph on the left, which represents normal distributions. This distribution is continuous and shaped like a bell curve, and it's centered around the mean. In this case, 170 centimeter, which represents the average height of people in this example. The shaded region shows 1 standard deviation above and below the mean again. So in a normal distribution, 86% of all data points fall within this range. But what does it mean? It means that most of people's highs are close to average, which is 170 centimeter. For example, if the standard deviation is 5 centimeter, the range will be 165 to 175. About 68 of people will have highs within this range. This is the part of the empirical rule, which I mentioned you before. And let's move to the graph on the right, which shows Bernoulli distributions. This distribution is used for binary outcomes like woman, man, or success, failure, yes or no, this type of data. For instance, as we told before, flipping a coin has 2 possible outcomes, heads or tails. So if the probability of heads is 0.5, then about half the flips will result in heads, and the other half will result in tails. And why is this important in machine learning? The Bernoulli distribution forms the foundation of binary classification problems, where we predict 1 of 2 outcomes. So, for example, another example might be like spamming, classifying emails as spam or not. So understanding these distribution is crucial in machine learning as well, because they allow us model uncertainty, make predictions, and evaluate our results. And normal distribution is often used in algorithms like linear regression and clustering because it helps us model continuous data. The Bernoulli distribution is key for models like logistic regression, which deal with binary outcomes. Let's dive into also probability theory. On this slide, we will talk about 2 key ideas, conditional probability and Bayes theorem. We use conditional probability when we want to know what is the probability of an event happening, given that another event has already occurred. Here is the formula for conditional probability, but let's look at some of examples. So the question here says, if a customer clicks on ad, what is the probability they will buy the product? So here, A is the event we care about, which is customer buying the product. B is the condition, customer click on ad. So conditional probability help us calculate the chance of A happening when we already know that B has occurred. Next, we have bias theorem. This is used to update probabilities when we have new evidence. And the formula looks like this. But I want to talk about the real world examples. Let's say, what is the probability that an email is spam if it contains the word win? And in the example, there are 100 emails, and we know 20% of them are spam. So probability of spam will equal to 0.2. But we know that 80% of spam emails contain the word win, which is a probability of contains win given spam will be 0.8. And we know that 10% of non-spam emails contain the word win, which is the probability of contains win given not spam will be 0.1. So we had 100 emails. So 20 emails are spam, and we know that 80% of them contains win. And when we multiply of them, we have 16 spam email contain win as a word. And the rest of 80 emails, we know that they are not spam. And we know 10% of non-spam emails contain word win. And when we multiply them, we have 8 non-spam email, which is contain win. So in total, we have 24 emails has word win. So the probability of seeing the word win in any email should be 0.24. So using bias theorem, probability of spam given win equals probability of win given spam times probability of spam, and all divided by probability of win. So basically, when we multiply 0.8 with 0.2, it will be 0.16. And when we divide by 0.24, we calculate as 0.67, let's say. So this means that there is 67% chance the email is spam if it contains the word win. So to wrap up, conditional probability help us find the probability of one event given that another event has already occurred. But bias theorem allows us to update probabilities using new evidence, like calculating the chance of an email being spam when it contains a specific word. But what is the difference between these probabilities? Basically, bias theorem help you to answer. I mean, bias theorem is helpful when you need to update or reverse probabilities. It works backward by using clues about B and to update your belief about A. So simple, let's say conditional probability, it's like saying, if I know the road is wet, what is the chance it's raining? But bias theorem is asking, if I know it's raining, how likely is the road wet? So let's move regression analysis, which is very important technique in statistics and machine learning. These methods help us model and understand the relationship between dependent variable or target and one or more independent variables or predictors. So on this slide, we will look at 3 types of regression: linear regression, logistic regression, and polynomial regression. And each of these has distinct applications. I will explain how they work and what these graphs represent. Let's start with linear regression. Linear regression is used to predict continuous outcome by finding a straight line relationship between the predictor and the target variables. For example, in the first graph, the blue dots represent actual data here, house sizes, and their corresponding prices. So the red line is a regression line showing the predicted prices based on house size. For example, if you have a house that 50 square meters, you can use this line to predict its price. This technique works well when relationship between variables is linear, as shown here. The next one is logistic regression, which is used for classification problems. Instead of predicting a continuous value, it predicts probabilities. For example, the probability of student passing in an exam based on their score. In the second graph, the blue dots represent actual data, whether a student passed 1 or failed 0. And the red curve is the logistic function, showing the probability of passing as test score increase. So you can see that as the test scores crosses a threshold around 50, the probability of passing sharply increases. So the logistic regression is widely used in binary classification problems. Like another example might be like predicting if an email spam or not. So when we are talking in logistic regression, I want to also mention about bias theorem that we talked before. I mean, what is the difference between these two methods? Maybe you have some type of questions. So, sorry. Bias theorem and logistic regression are used to estimate probabilities, but they different in their approach and purpose. Bias theorem calculates probabilities using conditional probability and prior knowledge. It's based on relationship between events. Logistic regression is a machine learning algorithm that models the probability of binary outcome, 0 or 1, based on input variables. So instead of manually calculating probabilities, using prior knowledge, like in bias, logistic regression learns the relationship from the data. This is the, basically logistic regression is data-driven model that learns the probabilities from the data rather than relying on predefined rules. So let's move to polynomial regression, which models nonlinear relationship. For example, in the third graph, we are predicting car mileage based on speed, and the blue dots represent actual data, different speeds, and their corresponding mileage. So the red curve is polynomial regression model, which captures the parabolic relationships between speed and mileage. You can see that at low speeds, mileage is high, but as the speed increase, mileage decrease. But as the speed increases, mileage decreases and eventually starts again increasing again. So polynomial regression is useful when data shows nonlinear trends like this. So each of these methods plays a crucial role in machine learning and enabling us to build models that solve diverse problems, from predicting house prices to determining whether a student passes or fails. I want to make a quick recap of key concepts we covered so far. I want to stick with one consistent example, rain. I believe this will help us to see how each method works and what was the difference between them. So first we have probability. It measures the chance of an event happening. So what is the chance it will rain tomorrow? Here, we just calculating the likelihood of rain, like saying there's a 30% chance it will rain. This is a straightforward prediction of one event. Conditional probability, this helps us to find chance of A happening, given that B has already occurred. Like if it's cloudy, what is the chance it will rain? So in this case, we know it's cloudy. That's our condition. And we are refining our predictions for rain based on new information. Bayes theorem, this where we take conditional probability and reverse the logic. Instead of predicting forward, we work backward from an observed result to determine the cause. For example, if it is raining, what was the chance it was cloudy earlier? Here, we already know it's raining, and we want to figure out the likelihood of cloudiness, the cause. And also, we talked about linear regression. We said this method predicts a continuous value using a straight line relationship between two variables. For example, how much rain will fall based on humidity. So if higher humidity leads to more rain, linear regression finds a straight line pattern to predict the exact amount of rainfall. And the logistic regression also we talked. It predicts probabilities for classification problems. For example, what is the chance it will rain based on humidity? Here, we are not predicting the amount of rain. Instead, we are calculating the probability of rain happening. If the model says there is a 70% chance of rain, we can classify the answer as yes, it will rain because it's a high percentage. And we talked about polynomial regression, which is used when the relationship between variables is nonlinear. It follows a curve instead of a straight line. For example, how does rainfall change throughout the day based on time? So rainfall might peak in the morning, drop in the afternoon, and rise again in the evening. A straight line wouldn't capture this. So, but polynomial regression fits a curve to show these changes accurately. So this sets the foundation for, we talk all the methods. Now we can talk about model performance metrics. So why do we need to evaluate the models? The goal of evaluating our models is to ensure it's accurate, and that is, it can also work well with new data when the new data comes in. So a model that performs well during training but fails with unseen data is not useful. That's why evaluation metrics help us measure this performance objectively. So we have different metrics, both classification and regression models. So for the classification part, we have accuracy, precision, recall, F1 score. And for the regression part, we have mean absolute error, root mean square error, or mean square error. And also I will talk about R square in the further slide. So for classification models, such as predicting whether an email is spam or not, we often look at precision, recall, and F1 score to handle imbalanced data sets. For regression model that I said before, like predicting house prices, mean absolute error or mean square error gives us insights how far of our predictions are from actual values. So the choice of metrics depends on the problem we are solving. For instance, in a medical diagnosis model, you might prioritize recall to minimize false negatives because it's more risky. While in a financial application, precision might be more crucial. So let's move and let's focus on first evaluating classification models. Mostly we are using confusion matrix for this. And the confusion matrix is really powerful tool for visualizing how well our classification model is. On the left, you see the confusion matrix, which summarize the performance of our model by comparing the predicted labels with actual labels. True positives, which means the model correctly predict the positive class. Here we have 4 true positives. And the true negatives, the model correctly predict the negative class. Again, it's 4 in this example. And we have false positives. These are incorrect predictions where the model predicts positive, but the actual label was negative. So in our example, there is 1 false positive here. And also false negatives. We have, there are cases where the model predict negative as a negative, but the actual label was positive. So 1 again in this case. So these 4 numbers are building blocks of key evaluation metrics. Let's first one is accuracy. Accuracy measures the percentage of correctly predict instance out of all predictions. So the formula is here. And in this example, the accuracy is, 4 plus 4 divided by 4 plus 4 plus 1 plus 1, which is 0.8. Let's talk about precision. Precision focus on the accuracy of positive predictions. So it answers the question of all the instances predicted as positive, how many actually positive? How many were actually positive? So the formula is here. In our case, it is 4 divided 4 plus 1, which is 0.8 again. We have recall also, which is sensitivity. Recall tell us how many actual positive case were correctly predicted. It answers the question like all the positive instances, how many did the model correctly classify? So the formula is here again, and the recall will be 0.8. Then we have also F1 score. It is basically the harmonic mean of precision and recall, balancing the 2 metrics. It's particularly useful when you want to evaluate a model's performance with both metrics, equally important. In this case, we have also 0.8 F1 score. So, sorry. In this example, all metrics are 0.8, which indicates balanced performance. However, these metrics provide different perspectives, helping us make a better decision based on a problem we are solving. For example, precision is crucial when false positives are costly, such as in spam detection, because an email was not spam, but we are predicting as a spam. Or recall is important when false negatives are risky, such as in medical diagnosis, because disease exists, but we test fail to, our test is fail to detect it. Let's move also regression models, metrics. So regression metrics measure how close the predicted values are the actual values. So these metrics help us assess the model's accuracy in predicting continuous data, such as house prices or stock values. Let's talk about first mean absolute error. It is the average of how far your predictions are from the actual values. For example, if you are predicting house prices and mean absolute error is 10,000, sorry, it means on average, your predictions are off by this value. When you want to use this, you can use this. When you want a simple way to measure errors, and you don't want to worry about bigger mistakes, so you can use this metrics. And we have also mean squared error. It is the average of squared differences between your predictions and actual values. But why square the errors? So squaring makes big errors stand out more. If your models makes a huge mistakes, so mean square error will highlight it rather than mean absolute error, more than mean absolute error. So we should use this matrix if we want to give more importance to big mistakes. And finally, we have also R-square matrix. This is very useful. These metrics tell us how much of the variation in the dependent variables, like house prices, is explained by independent variables, like size or house location. And basically, it shows how well the model fits the data. For example, if R-square is 0.85, it means 85% of variability in house prices is explained by the model. A higher R-square indicates a better fit to our model. To sum up, which metrics should I choose? So when you want to easy to understand average error, you can use mean absolute error. It's good for balanced errors. Mean square error, when you want to focus on big mistakes, because it makes large errors stand out more. And R-square, we should use this to check how well your model fits the data. So the closer it is to 1, which is better, it is better. So it is my last slide. I hope you like it. And thank you for your time and attention today. I hope you have a little bit more knowledge about statistics so you can build more powerful tools, machine learning models. Thank you for listening.
Thank you so much. It's a good overview, I think, of all of the important statistical concepts. Yeah, does anyone have any questions they'd like to ask? Lots of applauses and hearts.
And thank you so much.
I've got a question. So on the accuracy of things like binary models, logistic regression, that kind of thing, where you've got unbalanced data, so say you've got the outcome is skewed towards, like, let's say if you have a question around, you're trying to model whether, in a medical case, whether someone has cancer or not, out of the general population, most people aren't going to have cancer. So your observations, you're going to have more zeros than ones, which ones would denote you've got cancer. What's the best metric to use to evaluate that model when you've got unbalanced data?
So I think classification models can work, but maybe Parapa also have some ideas about this. But I mean, if I have a categorical values, we should use more, we can use classification matrix, confusion matrix, sorry. I believe.
Yeah,
but I think in general also that.
Sorry, go on.
Well, I would just say I think in general the F1 score is quite helpful if you've got an unbalanced data set.
Yeah.
Also, I think you can take the weighted average of the results, like for imbalanced data set, when you calculate the accuracy percentage on recall as well, you can weight it by the classes. So the class with like less number of samples can be given more weight as well. Does that make sense?
Yeah. Okay. Thanks.
Good.
Thank you.
Yeah, anyone else feel free to unmute yourself as well, or just post a question in chats. Yeah, I noticed a few people also saying thank you and also saying really helpful.
Thank you.
Yeah, thanks as well. Sorry, I'm completely congested. Yeah. All right, well, I can stop the recording maybe.